We spend a lot of time thinking about how our cells react to things, right? Like light or energy. But what if the real story, the real secrets, are found in what happens right after the stimulus is gone? Today, we're diving into the hidden echoes our cells leave behind, and a pretty cool new way scientists are finally learning to hear them. So this is a central question we're tackling. Imagine a scientist shines a special light on some cells. They see a response. Great. But what happens in those moments or even minutes after they flip the switch off? Does everything just snap back to normal? Or does a faint echo of that energy kind of hang around?
Okay, so a typical experiment like this has three parts. First, you've got the baseline. That's just the cells doing their thing, totally normal. Then comes stimulation, when the light or energy is on. And finally, there's this period that often gets overlooked, called the washout or recovery. This is where things get really interesting, and it's basically where our whole story begins.
Now, the problem is, studying this recovery phase has been, well, a real pain. For decades, it's been the source of a major scientific headache because the results have been inconsistent and often just flat-out contradictory.
And this has been a huge roadblock, especially in fields like bioelectronics. You'll have one lab report this amazing effect from, say, a pulsed electromagnetic field. But then another lab, trying to do the exact same thing, sees nothing. It makes it almost impossible to build on anyone's work.
So why is everything so muddled? Well, there are a ton of variables. Every lab might be using a slightly different energy waveform, or a different exposure time, or their cell samples might even be in a different biological state. Honestly, it's like trying to compare recipes where every single ingredient and cooking time is slightly different. You're never going to get the same cake.
So, to fix this mess, researchers are proposing a whole new toolkit. The idea is, instead of just looking at how big the response is, they want to listen to the quality of the system's recovery by measuring something they call coherence.
Now, coherence might sound a little out there, but they're using it in a very practical, very measurable way. It's not some philosophical concept, it's a number you can actually calculate. It's really just a way to put a number on how orderly, stable, and predictable a system is behaving, which lets you compare apples to apples between experiments.
And here's the really smart part. They don't just rely on one single measurement. Coherence is actually a combined score built from 4 different features of the signal. This makes the whole analysis way more robust. Let's break down what they are.
First up, they look at phase stability. You can think of this like a whole bunch of clocks that all get synchronized by the stimulus. The question is, how long do they all stay ticking together after that stimulus is gone? A high score here means the system's internal rhythm is super orderly. Then they measure the recovery half-life. This one's a bit more straightforward. How long does it take for the effect to fade away to half its original strength? A longer half-life means a more lasting effect.
Next, they go looking for hidden patterns. They measure the structure within the signal's decay. So instead of just seeing random noise as the system recovers, they're looking for subtle, repeating patterns, almost like a faint melody buried under a layer of static. And finally, they test its predictability. A highly organized, coherent system is less random, so its behavior should be easier to predict from one moment to the next. Basically, if a system is still ringing from the stimulus, it's going to be more predictable than one that's gone back to chaos.
All right, so with this brand new toolkit for measuring coherence, scientists could finally go searching for that elusive echo, that lingering fingerprint of the stimulus.
The experimental setup itself is actually beautiful in its simplicity. First, you record the baseline to get a sense of what normal sounds like for the cells. Then you apply your stimulus. And finally, the most important part, you switch it off and you just listen. You record everything that happens as the system settles back down.
Okay, now here is the key, the brilliant part of all of this. They don't just look at the recovery curve itself. They build a mathematical model based on that baseline data that predicts how this system should relax all on its own, with no special effect. Then they compare what actually happened to that prediction.
And this slide, right here, is the big reveal. Look at that dotted orange line. That's the model of how the system was expected to recover. Now look at the solid blue line. That's what actually happened. That shaded area between them, that structured difference from the expected path, that is the persistence signature. It's the echo.
So, in a nutshell, the persistence signature is a measurable, quantifiable fingerprint. It is concrete proof that the stimulus didn't just cause a temporary blip, but it actually changed the way the system organized itself as it returned to normal.
So you might be thinking, okay, that's a clever bit of data analysis, but this is so much more than that. Being able to find and measure this signature could have huge implications for how we design and understand all kinds of medical treatments.
What this framework really does is it lets us change the question we're asking. We're not just asking, did it work anymore? Now we can ask, okay, how did it work? How did the system reorganize its behavior? It gives us a much richer and more detailed picture of what's really going on inside.
And this is why it matters for all of us. This approach could help us design way better therapies. I mean, imagine being able to fine-tune light therapy to get the biggest anti-inflammatory echo, or optimize electromagnetic fields to help heal bones not just during the treatment, but long after it's over. And it could finally standardize research, making those inconsistent results a thing of the past.
I think the big takeaway here is this. Sometimes the most important information isn't in the loud, obvious response. It's in the quiet, structured echo that comes after. And by learning how to listen to that recovery period, we might just uncover some of the deepest secrets of how our own bodies truly work.